All right, thanks for coming today. Lunchtime talk. Before introducing our speaker, let me remind you of the event. On Friday, Bob Baderman from the philosophy department here at Pitt will be giving a lunchtime talk on deep learning, correlations, and the statistics of natural images. You're invited to Bob's talk. We begin at noon here. On Tuesday, Jim Tabry from the University of Utah, who is also a former graduate student in the Department of History and Philosophy of Science, will be talking at noon as well here at the center on the Black prisoners of Stateville, race, research, and reckoning as a dawn of precision medicine. So, the talk is the philosophy of medicine. And on Friday next week, there is no lunchtime talk, but we are sponsoring the talk organized by the Department of History and Philosophy of Science, which will be given by the Nobel Prize laureate, Jim Peoples from Princeton in physics. The talk will be at 3:30 in person only, so it will not be streamed. And the title is A Physicist's Philosophy of Physics. Peoples, as I just said, won the Nobel Prize. The physics department is aware that the man will be on campus, so it might be quite full. So if you are interested in the talk and plan to come, I suggest you come maybe 5 minutes again. It's on the 10th floor in the conference room here. Today, it's my pleasure to introduce Lucy James, who is currently a postdoctoral fellow with us at the Center for Philosophy of Science. We've been lucky to have her for now 2 months. She got her PhD in the philosophy of physics at the University of Bristol. Her advisor were Karim Tebo and James Lediman, and the topic was Has Metaphysics Done Its Time? She has published on that topic, Metaphysical Laws. And today, Lucy will be talking about primordial black holes in perspective. The floor is yours.
And thanks to the Centre for having me. It's been great so far. Yeah, really enjoyed it. So I think I said in my abstract that I was going to talk about matter formation. I'm not going to say very much about matter formation. If you're really here for the formation of matter and details of that, then my apologies. What I'm going to talk about
just click on the mouse once.
There we go. Okay, cool. So what I'm going to talk about, there's 2 parts to this talk. So I'm going to go with perspectival realism, which is this recently developed, very general view in the philosophy of science, and then try to apply some of the lessons from that view to the case of primordial black holes. So the second part of the talk is kind of going to be more like territory mapping. So looking at several related areas of physics to kind of get an idea of how they hang together, okay, and how we can try to identify their ontological significance. So looking at a few areas of physics kind of surrounding primordial black holes, and because they're studied from lots of different perspectives. So we'll have some things to say about that. A bit of background first. So it's roughly half and half general philosophy of physics and trying to get good metaphysics out of that. So a bit of background. I'm interested in the metaphysics of time, as Edward's introduction sort of made clear. How do we understand metaphysics? What's it all about? Well, I kind of come from the naturalized methods to learn metaphysical lessons. And what we find is that metaphysics gets kind of baked into physical theories. So there are assumptions, principles, background ideas about metaphysics that go into the formulation of theories. And then supporting empirical evidence for the theories can increase confidence in the metaphysics that goes into those theories. And then if there's falsifying empirical evidence or evidence that goes against the theory in some way, some kind of empirical anomaly, that's usually accounted for by modifying the theory in a way that does least mutilation to the metaphysics. So this implies terminology. It's about change the metaphysics as little as possible to account for the evidence. So primordial black holes, they play a role in theories that bear on the metaphysics of space, time, matter, and causation. Relevant physics for understanding primordial black holes and these areas of metaphysics. We've got general relativity, which is mathematically precise in some formulations, but it involves lots of idealization, which we're going to look at later on. So in particular, the singularities and infinities. So if we're thinking of metaphysics as a discipline that tells us what the world is like, these idealizations, mathematical idealizations, can be a problem. It seems like something that is done to make the theory work, but we can't read off in a straightforward way what that tells us about reality. Astrophysics is more data-driven, but it's less precise, and the data is theory laden. So that's another area. We're looking at this relationship between mathematical theory and data. Cosmology is involved, so primordial black holes being black holes that formed in the very early universe, shortly after the which is explanatory. But it's speculative and disunified. There are many different cosmological models that all seem to be empirically adequate, say data. They explain things in different ways. They explain why the data looks like it does in different ways. And then quantum gravity is also relevant, which is supposed to be unificatory, but radically underdetermined. So it's kind of well known by now that there are many different approaches to quantum gravity. So the theory that's supposed to unify quantum mechanics or quantum field theory with general relativity. There are many different approaches that theoretical physicists are working on, but there's no correct solution to this problem code. So the kind of scope of this, what we learn when we learn about metaphysics in this way, so from a kind of naturalized approach, what we get from looking at physics is we get provisional information about constraints on modal structure, often in the form of just heuristics that guide the next phases of scientific, in this case, physical inquiry. So metaphysics, in part, we're learning something about reality, but what we're learning is quite minimal. So we're looking at ways of constraining possible measurement. That's the way that I see metaphysics being used in science. So Lederman and Ross apply naturalized metaphysics to some things in quantum mechanics, and they use information theory, and that leads them to the structural realist position, which has some similarities to the perspectival realist position that I'm going to be discussing. A feature of structural realism is scale relative ontology. So depending on the scale, so that's length energy scales, you get different ontologies. Okay, so if you think about the quantum classical split, you have completely different things going on, different ontology if you're looking at the micro scale as opposed to sort of medium scale phenomena. If we're thinking about the ontology of space and time, though, a scale relative ontology is a little bit more difficult to articulate because space and time provide us with very important notions of what we mean by scale. So if we're saying ontology is scale relative, how we understand space and time is relative to the scale of this kind of similarity. So I think there's something right about what they're saying. We're going to sort of use these rough ideas to supplement and hopefully develop perspectival realism so that it can be used here, but not necessarily to length, energy, time scales. So instead, we can consider perspective relative ontology. Just say a couple of things about this, which you'll hopefully become clear as we go along. The idea that ontology is completely relative to the perspective kind of doesn't make full sense to me. So if we have different ontologies and different perspectives, I think it's still important to tell a story about how these different ontologies understood within different perspectives, how they hang together. Okay, so there's still some kind of unificatory idea going on in the background. But what is a perspective? Okay, so we know what scales are. What is a perspective? That's something. One example of a kind of perspective to start off then might be a metaphysical perspective. We've said a little bit about the use of metaphysics in science, but where do metaphysical principles come from in the first place? Sometimes from folk intuitions. So, for example, space is flat, three-dimensional. That's kind of an intuition that we might have about space. And there's some kind of deep distinction to do with the way that we directly experience things. More robust metaphysical principles might come from just what's associated with successful scientific theories, so past successful theories. And this is really in line with the naturalized metaphysics approach. So what's associated with successful theories is then what we take to be metaphysically serious. So for example, we have hyperbolicity, locality, separability. These are all metaphysical principles that I'm interested in, which are associated with past successful theories of space and time. Another source of metaphysical principles might just be what's conceivable. So imagining beyond successful scientific theories. For example, this might be slightly contentious, but for example, that the Earth moves for Copernicus, in his day, this was quite a radical thing to say. That wasn't associated with past successful theories. It was a new revolutionary idea. And then more relevant for what we're going to be talking about later, we've got primordial black holes with a radius that's double the Planck length. So we've got these very, very, very tiny primordial black holes, which are too small to be measurable. And then there are some cosmological ideas that we're going to be looking at as well, which go beyond what science is actually telling us. What I take to be the aim of metaphysics is to find out what's necessary a priori, so kind of Kantian, thinking about what's responsible for the success of past theories. So this is more difficult than just looking for what's associated with past successful theories. We're looking at what's actually responsible for that success, and then distinguishing between the metaphysics that's just there contingently in theory, and the metaphysics that's actually responsible for the success, and therefore is required for the success of future theories. Hopefully I'm making some sense. So as an example, we're still speaking kind of roughly here, we're still on the general part of the talk. But just a rough example, we can think of general relativity, whatever your favourite formulation is. And we can think of this theory as, in its early form, as an extremely permissive, minimal set of metaphysical principles that get encoded into the Einstein field equation. Okay. So we can think of some kind of equivalence principle is baked into the Einstein field equations. And the solutions, each of which represent a possible model of what space and time could be like. So Hawking and Penrose, sort of mid to late 20th century, they add more to the theory. For example, cosmic censorship conjectures. And this plays the role of restricting what is deemed to be physically reasonable. So they add more metaphysics basically to it, certainly in Einstein's theory, get more specific results. And the theory has a high energy cutoff beyond which something must change. So we've got this, these regions of space-time, which we can't say anything about using general relativity. So that leads to extremely speculative physics. So I've mentioned already that there's a plethora of different approaches to quantum gravity. And each different approach, each different kind of speculative approach to what happens beyond the high energy cutoff of relativity theory will lead to a different kind of metaphysical interpretation. There are different metaphysics associated with different approaches to quantum gravity and cosmology. So thinking about what happens below the 5 scale. Here, it's not showing up for some reason. Hopefully, my other pictures do show up. But I was going to put on just a picture of the whole universe. You might have seen before, like where it starts very, very small and then it comes out as a cone and gets bigger, right? So it's got this period of rapid expansion called inflation, right? So it's very, very quick. And it starts off below the Planck scale, right? So there's a time at which the universe were smaller than the Planck length, so empirically inaccessible. And inflation is this mechanism that's hypothesized to make the universe grow very, very quickly to a size that we can then start to get empirical data about. We'll say more about those things in slightly more detail later on. But when we're thinking about this, just to give a bit of an idea, when we're thinking about these speculative theories of physics that go beyond the Planck scale, we have multiple different perspectives giving us different kinds of information. So perspectival realists, Guilleri, Teller, Massimi, claim that roughly all knowledge is perspectival like this. So no matter what item of knowledge you've got, it's always possible to construct an alternative perspective that would assign a different truth value to that claim. So it seems clear that this is true of very, very speculative physics, right? You can have one cosmological model, you can construct an alternative that accounts for the data equally well. You've got different perspectives. But these guys are claiming that that's the case with all knowledge. So it's a bit of a weird view, but not totally wrong. Not totally wrong. So another way of putting this is kind of just nice language, really, to describe the situation from Hugh Price. He talks about no fault disagreements between different perspectives. He applies it to quite specific situations, looking at causation and temporal asymmetry. But these other perspectival realists want to apply this thought to all of knowledge, where we've got different perspectives making different claims. Neither one is better or more correct than the other. Right, so there's a couple of examples of, so there's kind of two different camps of people who use this idea of perspective relativity in the literature. So we've got Guilleri, Teller, Massimi, and co, and then we've got Hugh Price, Sam Barron, Pete Evans, who use the same kind of idea but in more specific situations to show where there's an alternative perspective. So I take certainly Sam Barron and Pete Evans. I'm not so sure about Hugh Price, but Sam Barron and Pete Evans certainly don't want to apply this perspectival stuff to all of knowledge. They want to show that there is these specific cases where alternative perspectives are just as good, and then that particular claim is less certain than was maybe thought. So, yeah, these ideas have been kind of developing over a period of time, several years. On the side of the perspectival realists, with this very general philosophy of science, it kind of culminated in Michaela Massimi's book. Some of her inspiration does come from the kinds of cases that I'm thinking about in cosmology and astrophysics. But then she went and looked at lots of different areas of science as well. So a benefit or a problem, kind of the generality of the view. For me, I think it's turned out to be a bit of a problem. So if you want to say something about epistemology, methodology of the whole of science, it's very, very difficult to say something that's precise, that's clear, that also achieves that level of generality. Right. So I was coming to this and looking for something that I could then use, looking for a tool that I could use. Rereading this book, I don't think that was kind of the intention really. I think the intention was more descriptive to say how science carries on. It's not a bad read. Like I'm not recommending it. I did find that I had to kind of slightly put to one side high demands on rigor and logical consistency. It's a genuine review, right? That wasn't meant to be funny.
That makes it even more damning.
It's a good read, though. Like, it's not bad. It's got some nice metaphors. Right, I'll stop doing that. Some key points from the book. It's kind of summing up. So just sort of reading lots of it, not focusing on the details and pulling out some things that I'm trying to make useful. All right. So it expresses a form of relativism. Knowledge is relative. Fair enough. Scientific perspectives are privileged due to their reliability. So it's not the case that all perspectives are equal. We have different perspectives which have different qualities. Scientific ones are reliable, so that's sort of better or makes them more worthy of study. Realism is asserted, and part of the way that this is discussed is that there's a distinction made between methodological justification for knowledge claims and truth conditions. So the justification for claims made by a perspective is local to that perspective, but the truth conditions which tell us whether the claim is right or not, that goes beyond the perspective. So we've got some kind of reality of was hoping. Never mind. So the situation is a little bit like this, right? So we've got one reality, there's a sense in which this is all one picture, but depending on how zoomed in you go, so how close or how far away you get different information, different knowledge, you describe things in different ways. So we've got epistemic and semantic differences depending on whereabouts you are, what perspective you've got. So this is just to give some intuition on what I take Michaela to be saying. Empirical access to the world varies with perspective. So when we're asking what is a perspective, we're thinking it's the kind of thing that gives us differences in our ability to access the world empirically. Representations of the world also vary with perspective. So how we describe the world, how we represent it mathematically, how we might draw a picture of the world. This also varies with perspective. What is a perspective now? Well, it's anything that gives us a different way of representing the world. And then the bit which is not totally clear, is reality itself supposed to depend on the perspective? It seems in different parts of the book, sometimes she wants to say, yes, reality is perspectival as well. We've just got these different realities, depending on how we're looking at things, how we're modeling things, how we're measuring things. Other times she seems to want to say there is a unified reality out there and we're just observing it or representing it in different ways. I kind of lean towards the latter interpretation where there is a reality, we understand it in different ways. And then, so me reading her wanting metaphysics from the view, I mean, I was maybe misled by the title and some of her earlier papers. With realism in the title, I thought she was going to tell me something about how to access reality, what is real according to the view. But it doesn't, and she sort of catches this. So she says, perspectival realism, as I articulate it in this book, is not a metaphysics first view. It's a project in the epistemology of science. So maybe I'm being a little bit unfair to her where I'm saying there's no metaphysics. How do I know about metaphysics? How do I know what's real? It wasn't actually intended to give that kind of guidance. It's just about knowledge. Different aims to what. And we should just say a little bit about this. So a little bit about how to access reality. She talks a lot about model dependence and models being a kind of perspective. So the plurality of models is explanatory in enabling a particular kind of inferential reasoning that feels fruitful when we want to explore what is possible. So notice that this is a modal claim, so we're thinking about reality being to do with what's possible. This exploration, I argue, is an important guide to what is actual in science. Indeed, it is often the only way to find out what's actual, given that we do not have a view from nowhere on nature. Okay, so a lot of the book is just pointing out that we don't have this view from nowhere. So we look at many different perspectives. We look at all of the views that we do have and unify where possible. These are the main methodological lessons. So just a few problems, questions for Masami. I've kind of mentioned already, does the relativism apply to only knowledge and representation? So are we just talking about perspectival disagreement being at the level of epistemology and semantics? Or does it apply to ontology, reality as well? And when we're looking into cosmology, this becomes quite important in trying to distinguish between epistemic and semantic disagreements on the one hand, ontological disagreements on the other, becomes a little bit more challenging. Is reliability a strong enough criterion to distinguish scientific perspectives? I don't think it is. So I have in mind here lots of perspectival information is reliable, but we wouldn't call it scientific, right? So every Tuesday and Friday there are bagels out there. It's reliable knowledge, right? But there's nothing scientific about it. So yeah, I don't think reliability is strong enough to say which perspectives are scientific. Maybe in some cases it's too strong as well. So if we're thinking about speculative areas of science, there's questions as to whether they really count as science, and maybe using reliability as a necessary condition can give us like a distinction between good science and like a line beyond which science is becoming too speculative. So it could be used as a necessary condition. If we want to consider speculative physics as scientific, then reliability is really too strong because it was always critical. What about perspectival disagreements within science? So this is again something that's really confusing in the book. A lot of her earlier work before this book came out was looking specifically at perspectival disagreements within science and saying these are different scientific perspectives. In the book, there's a line that I noticed that said scientific perspectives do not offer perspectival facts. Most of the rest of the book seems to be in conflict with that thought, so it's tricky. Yeah, problem. So a methodological justifications and truth conditions are always so clearly separated. So I have in mind here, kind of pave within a theory is just the same as its truth condition. Or say a methodological justification for a claim is the outcome of some proof test. That also serves as the truth condition. So I'm not sure that they're always so clear. Maybe this is not a huge central problem to review for this. Yeah, it's there. And then relating to the first problem, does perspectival realism give us any better understanding of what is actually real? Problem solved. This might be a bit quick, but never mind. So does the relativism apply to reality as well? So here I'm not trying to interpret massively anymore. I'm trying to indicate that I'm interested. So maybe, I mean, we have to look at the details of specific cases to decide whether the relativism applies to ontology as well as semantics. Is reliability a good sort of demarcation criterion? As I've said, I don't think so, but maybe perspectival realism doesn't need to be tasked with solving the demarcation problem. So we can have reliability being a feature of that distinguishes other kinds of perspective. Disagreements within science, let's try to resolve them. The scientists themselves do this in some cases, but when we have multiple different research programs going on, I take them and say, well, where are these different research programs agreeing? Where are they disagreeing? Where do they, if they're working on the same problem set, where do their disagreements matter? What do their disagreements amount to? Trying to resolve disagreements within science. Methodological justifications and truth conditions, or maybe they're not always so clearly separated. Not sure that's too important. You might have some on what is real. This is Massimi's own word. She says that the approach proves fruitful and we want to explore what is possible, which is so from this we can take ontology to be modal constraints on possibility, which is in line with its view as well. And so how can we apply this to evolving physics in a way that could be methodologically helpful and metaphysically illuminating? So one way would be to seek continuity across perspectives. We look for perspectival agreement. So this is almost identical advice to what we find in arguments for naturalized metaphysics, where the idea is to seek continuity through theory change over history. The difference with perspectival realism is that the alternative perspectives can be synchronic phenomena, so they're different perspectives that all can coexist. As an illustration of seeking perspectival agreement between perspectives, if you haven't met these two before, they're Wallace and Gromit. They live in West Yorkshire and they like cheese. So they're deciding where to go away. They want to go on a cheese holiday. And Wallace, the man, says to Gromit, his dog, well, everyone knows the moon's made of cheese. So we've got perspectival agreement between this everyone, Wallace, the man, and the dog doesn't disagree. And presumably in the magazine that is reading, there might be something about the moon being a good holiday location. So then they go one step further. They do better than that. They quickly knock up a spacecraft. They can do that, they're inventors, and go to the moon. So seems like something's gone wrong, right? So we've got perspectival agreement between these multiple perspectives. Presumably, we don't want a philosophy of science that allows us to make claims or to take seriously claims like the moon is made of cheese. It's just a perspectival disagreement. It's just due to some epistemic or semantic difference. I want to say there's a real state of the moon that's not cheese-like. So Hasek Chang puts this point quite nicely. He says if we could step out of Plato's cave, we would only see maybe more spacious or better in some other way, and accordingly you can pity those left behind in the old cave, but only in a relative sense. We can never get out of all caves, and there is never going to be that one final escape into the ultimate sunlit reality. It sounds kind of bleak if we want kind of good, strong metaphysics that is not going to change. But the method is clear, right? So we unify ideas. When we step into a new, more spacious cave, we're still aware of the previous cave, right? So we can expand perspectives in this way. For example, we can become disillusioned and find out that these characters are made out of plasticine and the moon's not made out of cheese after all. So perspectival agreement, seeking agreement across perspectives, is one way of applying the lessons, but it has its limitations. Another way of applying perspectival realist lessons would be to examine features of the perspectives themselves, so to look for sources of disagreement. So if we just seek agreement across perspectives, then we end up in this situation where we can't step outside. If we look at the perspectives that are disagreeing, then we can choose not to take certain perspectives seriously. And I think we should be doing both of these things. So the first idea is very prevalent in Massimi's book. She kind of quite clearly recommends seeking this continuity, this agreement between perspectives, and sees that as being integral to scientific epistemology. She says less about examining features of the perspectives themselves, so looking for sources of disagreement. And then if we have both of these kind of methodological ideas in mind, careful inquiry into the practice of physics does actually allow for the distinction between merely epistemic and semantic perspectival disagreements, which I think are fine more or less, and disagreements about basic ontology, which are not fine, or at least we want some way of saying how these disagreements occur and how the different ontological pictures might hang together. So now we're going to try and apply all of that to the case of primordial black holes. So we've said some, there's going to be lists of perspectives at various places, right? So we've said something about metaphysical perspectives. We've said something about perspectives in general. Another way of thinking about perspectives would be as sub-communities within all the areas of physics that kind of deal with primordial black holes. So we've got astrophysics, classical relativity, mathematical relativity, semi-classical gravity, quantum gravity, and analog gravity. And all of these different areas of physics give or use different definitions of black holes and use primordial black holes in different ways. And we have alternative models within each of these perspectives, alternative approaches within each of these perspectives. And then to the primordial black holes, their existence isn't even endorsed by every single perspective that's on the table. So they're generally regarded as speculative because fewer perspectives agree on their theoretical role and whether they help with the interpretation of data or how they help with the interpretation of data. So Curiel recognizes this. He's got a nice paper that gives lots of different definitions of black holes. And he's got kind of a pragmatic approach to this, which is in line with what some of what I'm taking from perspectival realism. So he says that this profusion of different possible definitions of black holes raises problems that are especially acute for foundational work. But these are not insolvable problems as far as Curiel is concerned. he says most physicists know what a black hole is right up until the moment you blindside them to a definition. So this was his methodology for writing this paper. He went around and asked physicists, what is a black hole? And yeah, kind of collected what they said. So this is a case of semantic perspectival disagreement. In this case, the different definitions engender different approaches to empirical measurement, and they encode different beliefs about ontology that are associated with the different definitions. So in other words, the plurality of definitions of black hole amounts to more than merely semantic perspectival disagreement. So then what we can do is investigate the epistemic states of the perspectives that give these different definitions to reveal where the ontological disagreements can be resolved and where they can't. So here are some of the definitions. I've got them all on this slide. So in astrophysics, black holes are compact objects, regions of no escape, engines for enormous power output. I won't read them all because we'll be coming back to some of these and discussing them. So we've got many different definitions. Within each area of physics, we've got multiple different definitions that draw on different features, right? So in classical and mathematical relativity, the definitions have a more global quality, so they refer to infinity, singularities, whereas in the more empirically driven areas, they have a more operationalized definition. And in quantum gravity, it's like, so no good definition. Okay, and then analog gravity as well. So that's running simulations, so terrestrial simulations of what goes on. So astrophysics, looking out into space, analog gravity, and some of high energy physics as well without gravity, is modeling the very early universe, so simulating it to see what happens. Imagine like mad scientists with the little tiny models of the universe playing with it, seeing what happens, and how I understand analog. Physical or mathematical relativity, I'm just going to run them together for the purposes of getting through it. Black holes kind of existed in the 1960s for the general relativists before they were taken seriously by astrophysicists and cosmologists. And this came from studying Schwarzschild's spherically symmetric solution of Einstein's field equations, designed to model the final stages of stars collapse. So yeah, as I've mentioned, Einstein's field equations have many different solutions, each representing a possible space-time. If you put into them initial conditions that represent collapse scenarios, so the collapse of the star, then sometimes you end up with singularities and strange things. So two defining features of black holes, I'm trying to keep the discussion as non-technical as possible. So but two defining features of black hole according to relativity theory is there's the object, the astrophysical object, tends to zero. Other terms like curvature tend to infinity. And then there's an event horizon at the Schwarzschild radius. So there's a region beyond which signals can't get out of the region. Okay, so the gravity becomes stronger than the energy of the matter that's in the region. So early on in this research, there was a question of whether black holes could be just an artifact of spherical symmetry of the Schwarzschild solution. So that's a mathematical idealization. So if we're getting these strange results using a mathematical idealization, we want to maybe question what role the idealization is playing. Penrose worked on this. So his singularity theorems prove that we get something like black holes for more generic collapse solutions of the field. So that's kind of central to the singularity theory. And then this work, collaboration with Hawking, they come up with a definition of black hole which invokes this notion of future null infinity. So relativist's definition of black hole, we take the entire space-time manifold, right, and extract from it the causal past of future null infinity. So all of the points which have causal curves that connect them to the infinite future, they're excluded from the manifold and what's left of the black holes. So that's consistent with the language that uses incomplete null geodesics. So primordial black holes can be understood in this way as incomplete null geodesics that just get trapped very early on in the universe's history. This definition has global features, so we're talking about the whole manifold, future null infinity, talking about features of the whole of space-time in order to define these objects. Yeah, so using these definitions, it's hard to operationalize basically because of these global features of the definition. So it's impossible to find where the event horizon of a black hole is without solving the Cauchy problem for the whole future development of the surface. And no local measurements one can make can ever determine the location of an event horizon. So yeah, this just points to the difficulty with operationalizing global definition. But black holes have been studied by astrophysicists who are much more empirically minded. So in the early 1970s, it was when observational evidence for black holes started to come out. But it wasn't until quite a bit later that these empirically driven areas of science started to agree that any kind of black hole existed. So we want to operationalize these definitions. This way of operation, so the astrophysicists would draw upon modal features of the general relativity definition. So this is from Curian again. The astrophysicists' definitions of black holes talk about them being compact objects, regions with no escape, engines for enormous power output. So rather than having this kind of conditions on the whole of the space-time manifold and extracting now specific objects that exist out there that have these properties. And then in analog gravity, so that's like you're making black holes in bathtubs. They think of black holes emission, no escape, time, or for low energy modes. So again, it's this region where things don't escape. So how do we find out about this? Even these more operating measure a region where no signal can escape from, right? Challenging. There's a nice, fairly recent collection. Domojevsky and Lenkel have contributed towards it. A collection of philosophy of astrophysics from last year, which is really cool. So they discussed some of these problems, and there were lots of different contributing authors. Domojevsky and Lenkel, in particular, look at this difficulty with accessing any kind of black hole. So yeah, they claim that more direct empirical access to black holes is in principle possible, although currently they're only accessed indirectly. So Hawking radiation is the only emission effect, so that's thermal and is undetectable, but black holes can be coupled to other black holes or to hot matter in an accretion disk, so matter can collect around the outside of the black hole. And then there's a detectable shape of emission sourced by the gravitational field. So they leave imprints, so they can't look at the black hole directly, they have some effect on surrounding gravitational fields. So how can we detect gravitational fields? Coordinated observers could, for example, shoot lasers towards the black hole candidate and test whether their paths agree with the trajectories of the Mildews of the Primordial. So you take a mathematical model of a black hole and look at what it says about the region outside of that black hole, right? And then shoot lasers to that region and see what happens. So we're looking at the bending of light, that's one way. One could also test whether light is on the verge of being trapped in a certain region, how strongly a given region lenses light, what the shape of this lensing region is, whether frame dragging effects occur, and so on. So, yeah, gravitational lensing is a really important way for getting empirical information about black holes, that light bends around. And that can be predicted fairly precisely using the mathematical theory, and then yeah, experiments so far, the more recent ones seem to be pretty successful confirming the prediction. So for ordinary black holes, not the primordial. So yeah, there's a range of ways. The earliest ways of detecting black holes were using ultra-luminous X-ray sources. A bit later, they started to involve optical spectrum imaging and radio interferometry, so that's looking at thermal features. LIGO-Virgo detectors, so that's detecting the gravitational wave. Jamie Elder's got a really nice bit on how this works. Analog experiments where the mathematics is used and the data to make like a smaller situation. So kind of modeling what's expected and then seeing what happens as a result of that. When I say modeling in the case of analog experiments, it's building a simulation. So simulating the forces. Again, there's kind of a nice description in the philosophical literature about this, about what we can actually learn from simulations, whether a simulation can tell us about like deep space. So there's another new detector that's currently under construction called the Einstein telescope, designed in a similar way to the LIGO-Virgo, but it will be able to probe at a high degree of precision. And it is hoped that this stronger detector will be able to distinguish between astrophysical black holes, which are the ones that we can already observe or observe the effects of, and primordial black holes, which from the very, very early universe. So looking at the mass of the black hole, redshift distribution, eccentricity, and spin, more precision on these observables is hoped by quite a lot of people in the astrophysical community. It's hoped that this will be able to distinguish between astrophysical. So some of the current data is already being interpreted in terms of primordial black holes. For example, very, very distant supermassive black holes. So the current kind of understanding of how the universe evolved, there are some black holes that are far enough away that we can date them back into the early history of the universe. But they're too big to have been able to grow that much in the time just by accretion of matter. Right, so black holes get bigger when matter falls in, and they get smaller when they thermally radiate. So there are some very, very distant supermassive black holes, which are thought to be primordial, or at least have come from primordial black holes in some way, because they're too big. There's not enough time for them to have grown to that size. So that's sort of fairly compelling evidence for the existence of something like primordial black holes, or some of this talk about seeds of black holes. But in general, the observational evidence for specifically primordial black holes is weak, much weaker than for black holes in general. So do I talk about them? Well, they could make possible the detection of other effects. So they're kind of embedded in this theory that allows for other kinds of detection and other kinds of interpretation. And they play a theoretical role in understanding observations that we do have. So on the first point, Matthew says that insofar as the magnitude of Hawking radiation from an astrophysical black hole and the magnitude of the cosmic microwave background fluctuations are fixed by the nature of physical law, the impossibility of direct detection of Hawking radiation seems fixed with nomological necessity. So Hawking radiation, a strong prediction of general relativity, is not something that can ever directly be detected, except there's a way around this, which would be the discovery of primordial black holes, whose low mass. So that's the other thing about them; they can be very small. So their low mass would result in a Hawking temperature sufficiently high to emit direct detection. So different.
You just press one already.
Okay, I'll speed up a little bit. So, yeah, the possibility of detecting one thing and feeding to the possibility of detecting another thing. So, in terms of perspectives, Cretu offers a discussion of perspectival instruments with an optimistic take on the plurality of different kinds of information accessed by scientific instruments. So, again, different ways of measuring things. And takes this, like other perspectival realists, to be a positive thing. So we've got lots of different ways of collecting information when that information doesn't agree. Not always a problem. In more practical settings, disagreements between perspectival instruments can be a very bad thing. If you're wiring a house and you're measuring the strength of the electrical circuit, you want your instrument to be good. You don't want a different instrument giving different readings. That's impractical. But perhaps in the kinds of regime that we've been considering, it's less of a problem, but even there, perspectival agreement is sought. So, for example, the discrepancy between the data from analog experiments and the data is taken to indicate an incompleteness of the theory. So, primordial black holes play a theoretical role in understanding observations that we do have within the lambda cold dark matter model of cosmology. They help explain matter formation from the radiation dominated era. They help explain the inflationary mechanism to create the expected or needed entropic conditions, account for some of the dark matter. But lots of this is speculative, right? So this is a picture of just where the primordial black hole is, right? So this is very early universe, quantum classical split. Black holes that are observed get bigger, but then there's this weird thing going on with scale at the top, where we're looking far away, things are large scale, but we're actually looking at when the universe is very, very small. In quantum gravity cosmology, the understanding combines local and global features, which is kind of consistent with that picture where scale, the very small and the very large, sort of come together. Yeah, so then some things that we've already said more or less about multiplicity of definitions and it being particularly acute in these more speculative ways. So far everything has been within the lambda cold dark matter standard model of cosmology. So all of the astrophysicists that I've been considering work within that model, in particular with inflation. But it's got some kind of perspectival aspects. So often string theoretic concepts are used in the astrophysics community. So they're very much concerned with empirical data, but the way that they interpret that data kind of sneaks in language around brains and things like this. So string theory is an approach to quantum gravity at this stage, too speculative for it to count as kind of the only available model. And then inflation is not the only mechanism that can account for the low entropy early state, dark matter, ordinary matter, other phenomena. Inflation is also a process that goes faster than light, which seems to be at odds with causal locality and is untestable. But we're looking at an area where the aim is more about getting a complete story of our cosmic origins rather than just producing science that's empirically testable. There is an alternative to the Lambda-Goldbach matter model. So that's a whole model that involves inflation. So an alternative is Roger Penrose's conformal cyclic cosmology. And this has a different ontological picture associated with it. So here the perspectival disagreement is at the level of models and ontology. So these are like really, really broad ideas, so models of the whole universe and beyond, right? So give us different pictures of ontology. And different mathematical models are meant to directly represent the possible state of affairs. So this kind of disagreement at this level does certainly carry ontological significance. Essential to conformal cyclic cosmology is Penrose's observation that the past boundary of one space-time can be connected to the future boundary of another at the cost of conformal rescaling. This is, think of it, stretching the space-time metric. So shapes stay the same, sizes get different. So this edge of this would represent temporal infinity, go to infinity, and then that's joined onto a subsequent universe. So it's a multiverse picture where the universes have this connection to each other. So each universe is called an eon. They're each represented as relativistic spacetimes, each with an infinite expansion into the future, so there's no big crunches. And then this infinite expansion leads into the next universe or eon. Massless particles are not concerned with metric structure. They respect merely its conformal structure. So massless particles are supposed to travel through from one universe into the next one. So it's suggested there might be some kind of empirical content to this idea. So at the end of the eon, most of the matter will end up in black holes, which act as converting devices. They convert massive particles into massless particles by transferring energy from the matter fields to the gravitational field. And then, so that's kind of part of the mechanism for how it works. And idea predicts two kinds of empirical signature in the cosmic microwave background. So this comes in the form of detectable merger events, what's expected to merge. And then when we're thinking about different kinds of black hole, the astrophysical black holes of one universe become the primordial black holes of the subsequent one. So we've got primordial black holes again, but they're playing a very different role in this cosmology. But it's not clear at this stage whether there's any empirical test that can actually distinguish between conformal cyclic cosmology and more standard Goldbach matter model. Summing up now, so it went on a bit long, that's very unusual for me. I usually go over the time, not over. So what is a perspective? We've seen a few examples. In the cases I've been looking at, a perspective could be a measurement procedure, could be a mathematical model representing a set of possible measurement outcomes. It could be a mathematical model representing the possible state of affairs, right? So there's different kinds of mathematical models. The cosmological models are different to general relativity with a high energy proton. The former cosmological models represent states of affairs, whereas the more restrictive mathematical models represent possible. And then what we said at the beginning, perspective could be a metaphysical principle or paradigm, which involves some interpretation or design of any of this world. I did just eventually look at perspective in the dictionary. Particular way of considering something. So that's the noun perspective, or we can get or keep something in perspective, which means to think about a situation or problem in a wise and reasonable way. So maybe that's what we should try and aim for. And then some interpretations such as perspectival realism makes scientific progress. Yeah, I'll leave it there.
Questions.